Turbulence. It's all around us. From the swirling cream in your coffee to the raging storms on Jupiter, it's one of the most common, yet most complex, phenomena in nature. It's also been called the oldest unsolved problem in physics. For centuries, scientists have struggled to fully understand and predict turbulence. Even with today's supercomputers, accurately simulating the chaotic dance of a turbulent fluid, like air flowing over an airplane wing, or the churning of ocean currents, remains incredibly difficult. But now, there's been a breakthrough. A team of scientists has developed a new approach, inspired by quantum computing, that's making significant strides in tackling this age-old problem. Traditional methods of simulating turbulence try to calculate every single detail of the flow, which requires enormous computing power. This new method takes a different tack. Instead of trying to capture everything deterministically, meaning, with a fixed outcome for every starting point, it models the fluctuations in turbulence probabilistically. Think of it like this. Imagine trying to predict the exact path of every single leaf falling from a tree in a strong wind. That's nearly impossible. But you could predict the probability of a leaf landing in a certain area. This new approach does something similar for turbulence. The key is a mathematical tool called tensor networks, which is often used in quantum computing. Tensor networks allow scientists to represent the complex, multidimensional data of turbulence in a much simpler, more efficient way. It's like finding a clever shortcut to describe the overall pattern, without getting bogged down in every tiny detail. This simplification drastically reduces the amount of computing power needed. What used to take a supercomputer days to calculate can now be done on a laptop in hours. It's 1,000,000 times better at using memory and 1,000 times faster. Now, let's connect this to the idea of noise in a closed system. In physics, noise often refers to random fluctuations or disorder. In a turbulent fluid, those random swirls and eddies, the very things that make it so hard to predict, are the noise. Think of a sealed container filled with gas. The molecules are constantly bouncing around randomly, that's thermal noise. The more chaotic the motion, the higher the noise level, and the higher the entropy, which is a measure of disorder. Turbulence is like a much more complex version of that. It's a highly energetic, chaotic state with a lot of noise, a lot of random fluctuations at many different scales, from large swirling vortices to tiny eddies. While the new method doesn't completely solve the problem of turbulence, especially the challenge of capturing all those different scales, it does provide a powerful new way to analyze and understand the noise within these complex systems. It allows the overall shape to be calculated. This advance has huge implications. Better understanding of turbulence could lead to more efficient airplane designs, more accurate weather forecasts, improved artificial hearts, and even a deeper understanding of the plasma flows within stars. This research is a testament to the power of interdisciplinary thinking, bringing together concepts from classical physics, fluid dynamics, and quantum computing. It's a reminder that even the oldest, most challenging problems can yield to new approaches and innovative ideas. And while turbulence may remain unsolved in the strictest sense, this breakthrough represents a significant step forward in taming the noise and unlocking the secrets of this ubiquitous and fascinating phenomenon.